All righty, gang. Good morning. Welcome back. Congratulations on surviving the first exam. Look, it's done and you're still here. You're alive. We're all still breathing. It's a fantastic thing. We're getting through this mathematics class and it is going to be better from here because now we've kind of done the whole gambit. You've done some homework, you've done some quizzes, done some activities, some projects, and a test. You now know everything this class can throw at you. It's just a matter of picking up the little bits of content that come. Today we are going to start talking about something called proportionality, which is a very big deal in the natural sciences, especially in physics, when you want to sort of understand the relationship between two objects or forces. One of the nicest relationships you could possibly have is a proportional one. So today we're going to talk about this notion of proportionality. I'm going to show you a whole bunch of problems. Before we do that, I want to talk just a teensy bit about the test. And then we'll get to it. If you missed the test for whatever reason, I did get some emails about this, like unprepared or sick or whatever. If you missed the test for whatever reason, I will be doing a makeup session. Just reach out to me. Some of you I've emailed already. Some I think I haven't had a chance to speak to. But if you missed the test for whatever reason, don't worry about having or not having a good excuse. Just reach out to me so we can figure out when to get you to take the test, because I want you to take the test. Before we get into stuff here today, there is a new assignment in Canvas. Now here's project one. Hopefully you've all handed in project one. If you haven't handed that in, please get it in as soon as you can. The exam one written work, I'm going to be going through this over the next week. My general rule on getting a test graded is 1 week. So you took the test on Thursday and I will have your scores updated with the partial credit from your written work by this Thursday. The new thing here is the test one reflection. This is, let me see if I'll show it here. It's in there as a Canvas quiz. And the purpose here is to help me understand what worked and didn't work for you, and to help you understand what worked and didn't work for you, so that moving forwards we can do more to help things go better. Or if it went well, we can do more to keep things going well. So I'm not going to put a due date on this, and it is worth 12 points in Canvas. That's not because there's a grade element to this. But it's because the way the college has it set up, there's something called the DLP, the Digital Learning Plan, that they need to keep some uniformity to the way they do these things. But I will count this the same as a quiz in my open math. That's the way we'll do it. So I will put the grade from that into the grade book in my open math. And it's, if you do it, you're going to get full credit on this. It's not something you can get anything wrong on. But I do need you guys to do it. I'm not going to put a due date on it, but the sooner you do it, the more helpful it will be. Just come into Canvas, go ahead and answer these questions, and share anything that you think might be helpful. That would be really nice. Okay. That's out of the way. This thing talking to me. Here. So this is, as always, MAC1105. Section number 15, which is college algebra. And the date today is the 8th of February 2022. Today we're going to talk about proportionality. There is a new homework and a new quiz open for you in my open math. It's just the one. It's due on Thursday, and the topic is, proportionality. So, yeah. So, tell me, has anybody heard the term proportional before? If I tell you that my weight is proportional to my height, what does that mean? Or if you've heard the term in some other context, share that with me. Let me know what this word means to you if you've encountered it before.
Like even?
Evenness or balance?
Fits best with.
Yeah. I'm sorry, what was that last one, Macy?
Fits best with.
Yeah, these are all good terms that come to mind for me when I think about proportionality too. There are two things that kind of grow together or shrink together, right? So if I say my weight is proportional to my height, I mean that as my height goes up, my weight goes up. As my height goes down, not that that happens, my weight goes down. Um, so two things that kind of grow or change together. And specifically, and this is our definition, um, we say that x is proportional, and I'm going to add a qualifier here, directly, meaning directly proportional to y if x is equal to some constant times y. That's the definition. So when I say that two objects or variables are proportional to each other, it means that one is equal to a constant times the other. There are a lot of ways to modify this language to give one of these two things a power. And we're going to get into a little bit the difference between what's called direct and inverse proportionality, but this is the basic idea. And sometimes this is denoted, especially in physics, with this like fish looking symbol, x fish y. These this is the equation, that is the definition. Sometimes you'll see people say that x is proportional to y by drawing this Greek letter alpha between them. Usually it's drawn with kind of a long tail to make it look a little bit like a twisted up equals sign. If you see this, this is what it means. I will not ask you to use this notation. You don't need to use this notation, but if you see this, that is what it means. It's possible also to say that x is proportional to a power of y. I could say x is proportional to y squared, or x is proportional to the square root of y, things like that. Before we play around with that, though, I just want to look at a handful of kind of very straightforward examples and give you a feeling for how most of these problems go. So for example, in children under 5, height is proportional to height, I should say, in feet, or let's say in centimeters. Height in centimeters is proportional to age in years. And then I could tell you that, or say, if a 2-year-old child is 90 centimeters tall, how tall will she be at 3 years? All right. So just a toy example, I'm not claiming this is actually true, but this is how proportionality problems are usually phrased, right? So you're given kind of an introductory sentence here, which tells you the proportionality relationship. And then you're asked a question prefaced by the information you need to find this constant. So the idea here is that you can set up an equation like this, but we don't necessarily know what this constant c is. The bit of information they tell us here, that a 2-year-old child is 90 centimeters tall, is what we need in order to find the constant c. Once you have this equation and you know the number c, you can plug that number in and you have an equation that tells you exactly what the relationship is between the two variables. And from there, you can do anything. You can solve or answer questions. So let's try this one. I'm going to go ahead and let height be the variable h, and let the age, let's do y for years. We're told that the height is proportional to the age. So h is equal to c times y. right? Just like x is proportional to y means x equals c times y. If height h is proportional to age y, then h is equal to c times y. Now they told us a 2-year-old is 90 centimeters tall. So they've told us when h equals 90, y equals 2. Right, 2 years old, so age y is 2. 90 centimeters tall, so h, the height, is 90. So then we can plug that stuff in. I can plug in 90 for h and 2 for y. And I can use this to solve for c. And that's going to tell me what the exact relationship is between height and age in this problem. So if I divide both sides by 2, 90 divided by 2 is 45. So I learned that the constant c is 45. And now I can plug that back in here. So the exact relationship between the height and the age in years is h equals 45 times y. This is all the work we need to do at the start to get ready to solve the problem. Now that we have this fully informed equation telling me exactly what the relationship is between h and y, I could answer any question. If you want to know, how tall will I be when I'm 4 years old, or how tall was this kid at 1.5 years old, you would plug in that age for y. If you want to know at what age will the child reach a certain height, you plug in that height for h and solve for y. So any sort of questions you could ask about a system like this, you can solve, but only after you find the constant of proportionality. So see this number here, it's called the constant of proportionality, or the constant of variation. To finish things up, I want to know, how tall is she going to be when she's 3 years old? So at age 3, we expect she will have height h equals 45 times 3. We're just plugging in 3 for y. And 45 times 3, what is that? That's 90 plus 45, 135. And that's in centimeters, or 1.3 meters. A little over 3.5 feet. I guess closer to 4 feet. Okay. So all of these problems have this feel to them. You're given the information that tells you how to write down the proportionality argument. You're given a little bit more information that allows you to solve for the constant of proportionality. And then you're asked a question. And you answer that question by first finding the full relationship with the constant of proportionality plugged in, and then either solving or plugging in for whatever it is they ask you for. So we'll grab a few more problems from your homework, something that is simple, and then we'll look at how you can complicate this relationship a little bit. Any questions about what we just did or the terminology we were using? Okay. I like this question too. This is fun. I'll change the numbers just a little bit because I want to play around. So the current exchange rate for US dollars into Mexican pesos is about 20 to 1. Let's see if we can structure a problem like that homework question in this way. So the value of US dollars is proportional to value in Mexican pesos. if, and how do we want to do this? Let's say, let's go $5 is equivalent to 100 Mexican pesos. What is the value in Mexican pesos of $30? We just want all right. So we're starting off here by being told that US dollars in value are proportional to Mexican pesos. So there is a relationship, a direct proportionality relationship between US dollars and Mexican pesos. Then we're told that $5 converts to 100 Mexican pesos. Finally, we're asked, what would we get if we converted 30 US dollars into Mexican pesos? So first we need to define our variables. This is something you always need to do with these problems unless they're specified for you. Sometimes they will be specified for you, sometimes they won't. So for US dollars, let me just use X and Y. What's the Y be the value in Mexican pesos? Both use the dollar symbol, so we're a little stuck on choices of variables. Then the proportionality relationship between these two things, they told us that US dollars is proportional to Mexican pesos. So X is equal to some constant C times Y. Nothing crazy. They told us that $5 US is equivalent to 100 Mexican pesos. That means when I plug in 5 for X, I should have 100 for Y, and that will allow me to solve for C. So 5 is equal to C times 100. Therefore, dividing both sides by 100, you get 5 over 100 equals C. And we can clean that up a little bit. 100 is divisible by 5. So if you write the bottom as 20 times 5, you see that the 5's cancel. And that gives us 1 over 20 for C. Now we can update our equation with the value of the constant of proportionality. So when you hear that term, constant of proportionality or constant of variation, they're talking about the constant in this equation, C. So C, we just learned, is 1 over 20. So X must be 1 over 20 times Y. The last thing we were asked to do is give the value in Mexican pesos of 30 US dollars. So when X is equal to 30, we can solve for Y. We get 30 equals 1 over 20 times Y. And then if I want to solve for Y, I just multiply both sides by 20. 20 times 30 is 600. And that's it. So 30 US dollars, about 600 Mexican pesos. And you see, it can kind of go both ways, where at the end you just plug in and get your number, or at the end you have to solve after you plug in. It depends on what's being asked for, which one of the variables they're asking for at the output. Questions on either of these or the terminology? I'm going to give you some slightly more challenging stuff in just a second here. I want to make sure we're real comfy with this. Okay. So even direct proportionality, before we touch something like inverse proportionality, can be a little bit more complicated. It is possible to have proportionality relations between powers of variables. So some simple examples here. The area A of a circle is proportional to the square of its radius. Give a little bit of space. I'm just going to list a few things like this. The time it takes, time t, it takes for an object to fall from a height h is proportional to the square root of h. Okay, so I have here two direct proportionality relationships, and I just want to see if we can write down the equation that's being described by these. And then we're going to do something fun with each one. Both of these are true statements, by the way. I'm not just making up random bullshit. If we say that A is proportional to the square of R, that means A is equal to some constant times, not R, but the square of R, which is R squared. Now, you probably know what the constant of proportionality is here if you're paying attention in high school geometry, but don't worry, we'll come back and play with this a little bit more. Before we do that, let's look at the second one. We're told that the time t it takes for an object to fall from a height h is proportional to the square root of h. So t is proportional to the square root of h. That means t is equal to some constant times the square root of h, like this. A big part of what makes these problems challenging is just taking the language, just taking the English language sentence and translating it into an equation. So before I do anything with these, are there any questions about where the purple stuff came from? Or how we knew to write those things down in that order, anything like that? Okay. Then let me go just a little bit further. Suppose a circle, cannot think today, of radius 3 has area equal to 9 pi. What is the constant of proportionality from the first example. So we were already told that the area is proportional to the square of the radius r. In other words, a is equal to some constant times r squared. And now we're told that a circle with radius 3 has area 9 pi. So we're going to begin with this a equals c times r squared and just plug those values in. The thing they're asking for this time isn't the answer to some other deeper question. They're just asking what's the constant of proportionality between the area and the radius. So if I plug in 9 pi for the area, c is still just c, that's what we're trying to find, and 3 for the radius, then we get 9 pi is equal to c times 9, because 3 squared is 9. And dividing both sides by 9, we get pi is equal to c. So the constant of proportionality there is pi. Let's try to do something fun with the second example. There are a lot of problems you can solve or questions you can answer here without even finding the constant of proportionality. I could ask you, if I increase the height by a factor of 4, what happens to the time it takes the object to fall? The constant of proportionality here turns out to be the square root of 1 over g, where g is the gravitational acceleration on Earth. But we don't need to know that to answer this. Let me go back just a second here. I'm sorry. So down here, we were finding the constant of proportionality from the first example. They told us a is equal to some constant times r squared, that the area is directly proportional to the square of the radius. And they just asked us to find the constant of proportionality, to find the number c. And the information they gave us that told us how to do that is they gave us the radius and area of a specific circle that I could plug in. So they told me that a circle of radius 3 has area 9 pi. Of course. All right, let's try the second piece here. So I don't know what this constant c is. Like I said, it turns out to be the square root of 1 over 9.8. It's a weird thing, but that's just here on Earth. That's how fast things fall. That's the gravitational acceleration. But without that information, I can still answer cool questions like these. If I increase the height by a factor of 4, what happens to the time it takes the object to fall? So before we do anything with this, I want to ask you, is the time going to go up or go down if I drop the object from a height that's 4 times higher? Right? Maybe I drop it from my desk, it takes some time. I drop it from a height 4 times higher than my desk. Is that time going to increase or decrease? Yeah, it's definitely going to go up, right? If I'm dropping the ball from higher, it's going to take longer to fall. That makes good intuitive sense. And it's wise to ask yourself these questions before you begin. Now, what I don't have is the sort of information we were given down here, right? Here they told me a specific radius and a specific area. Here, nobody's told me that it takes so many seconds for the ball to fall from such and such height. I don't have that. They said if I increase the height by a factor of 4, what happens? Increasing the height, increasing h by a factor of 4 means what? What does that language mean? If I say I'm going to increase something by a factor of 4, what exactly am I doing? Is that adding 4 to the height? Is that raising the height to the 4th power? Algebraically, increasing something by a factor of 4 means what? Suppose I told you I'm going to increase your salary by a factor of 4. What does that mean? It's an increase and 4 is involved, but yeah, multiplication is the thing here. And it's a little bit subtle, but remember what factoring is, right? Like when we talked about factoring quadratics, it means writing the quadratic as 2 things multiplied. So this word increasing by a factor of 4 indicates that you're multiplying the height by 4. So if I say I'm going to increase your wage by a factor of 4, that means I'm going to pay you 4 times what I do right now. And if I only added $4 to your wage, you'd probably be pissed because multiplying by 4 is considerably more than adding 4. So this means we're going to replace the original height, replace the height h by 4 times h. And they asked us, what will this do to the time? We said already the time is going to go up, right? If I'm dropping from a higher height, if I go from 10 feet to 40 feet, it's certainly going to take longer. So let's take our proportionality relation, t equals c times the square root of h. But instead of the square root of h, we're going to write the square root of 4 times h, because that's what it means to increase the height by a factor of 4. And they asked, what does this do to the time? Well, let's see if we can simplify. So there's nothing I can do with this c, but the square root of 4h is the square root of 4 times the square root of h. And the square root of 4 is 2. So this is t equals c times 2 times the square root of h. And now the trick is to find the original equation. All right, let me copy it down up here. Remember what we had? We had t equals c times the square root of h. The trick for these problems is after you've done what we did here, where you replace the variable h by 4h, to try and find this original equation hiding inside the new one. We want to compare this to this, specifically the right-hand side. I'm not going to do anything fancy here. I'm just going to write c times 2 times h as 2 times c times the square root of h. And then we compare the original thing, c times root h, to this thing, 2 times c times root h. So what has changed? What is the relationship between this new time and this old time? One is bigger.
It's double.
It's double, yeah. So if I drop the thing from 4 times higher, it will take twice as long to fall. That's the idea. So even if I don't know, if I have no idea how long it took, like I didn't measure, I can tell you that if you increase the height by a factor of 4, if you go from 10 feet to 40 feet, it will take twice as long to fall from 40 feet as it did from 10 feet, even if you don't know how long it took to fall from 10 feet. That's kind of cool, right? We can get this genuinely meaningful result without having any specific numbers to plug in. And that, I think, is very cool. And it's really this which is at the heart of proportionality. Having a proportionality relationship tells you how two things change together. There's a classic example from Walter Lewin's first lecture at MIT 801, which is their first physics with calculus class, where he talks about how the mass or weight, if you want to think of it like that, of an animal is proportional to the cube of its height. So roughly, if you have an animal that is, twice as tall, then the mass will be 2 cubed or 8 times larger. And he uses this to argue that, animals of a certain size can't exist because then their bones would break, right? They become too heavy. All sorts of cool things can be cooked up by starting with a proportionality relation like this. I'd like to do one more thing along these lines. Let me say here, recall from our previous example, from our circle example, that A is equal to pi times r squared. We found that that constant c was the number pi. If we double the radius, what happens to the area? So very much the same sort of thing that we just did. Here we do have the explicit relationship. We know the constant, but it doesn't matter. How do I answer this? What are they asking me to do? Which variable is going to be replaced by something else? A or R? Like in the last one, I replaced H by 4H. Here, I'm going to replace some variable by some other form. Am I going to replace the area by 3A or the radius by 5R?
Radius, we're finding the area.
Yeah, exactly. So I want to double the radius. That means we're going to replace R by 2R. And doing that, I get A equals pi times, and you need to be careful with your parentheses here, 2R all squared. And then like before, we're going to simplify and try to see the relationship between the new equation and the old equation. So 2R all squared is 2 squared times R squared. And 2 squared is 4. So this says A equals pi times 4R squared. And just like going from here to here, the trick was just to like shuffle the order around so I can see the original thing in there. This is the same as A equals 4 times pi r squared. So what's the relationship between this new equation and the original equation? Here's the original. Here's the new one. How
It's 4 times more.
Yeah, it's 4 times bigger. In other words, this pen. The area, let's use the language they gave us in the previous one, goes up by a factor of 4. Okay. So if you double the radius of a circle, the area doesn't double. The area actually doubles and then doubles again. It goes up by a factor of 4. So the area grows faster than the radius. That's the idea. All right. Now let me take a quick look at your new homework set, see if we're getting into inverse proportionality here, if it's all just direct and indirect. By indirect, he might mean inverse. Yeah, okay. So we do need to go ahead and introduce this second type of proportionality. So far, I've shown you here now everything you need to understand direct proportionality. Direct proportionality problems is really two types. The first type, where they tell you the relationship, you have to solve for the constant of proportionality and then answer some question by plugging in a number. The other type of problem you're going to encounter are the ones that we just did, where you're given the proportionality relationship, and then you have to describe how one variable changes as you do something to the other variable, usually multiply it or divide it by some number. The second kind of proportionality, remember I put the word direct in parentheses in that first definition. The second kind of proportionality, we say x is inversely proportional to y if x is equal to some constant times not y, but the reciprocal of y. Okay. And like the other ones, you can replace either of these with powers of variables. It doesn't have to just be the variables themselves. So inverse proportionality, direct proportionality describes two things that grow together. Maybe one grows faster than the other, like the area and the radius, but as one grows, the other grows. Right? It was this idea of balance, or things kind of moving together, that we talked about at the start. Inverse proportionality is the opposite. As one grows, the other shrinks. Right? So I could say that, my grade in this class is inversely proportional to the number of beers I drank, or something like that, right? As the number of beers goes up, the grade goes down, that sort of stuff. Let's take an example from your homework set, something where we can play with these in a gentle way. Well, sure, okay, I guess we can just start with something that has no applications. Suppose A is inversely proportional to B, and when B is equal to 6, we know A is equal to 4. Find an equation. Relating A. So they start off by telling me that these two variables, A and B, are inversely proportional, which means there's an equation like this going on. We start just by writing A is equal to some constant C times 1 over B. They also told us that when B is equal to 6, A is equal to 4. So we always start by writing down the proportionality relationship. Then if they give you some information that will allow you to solve for the constant, you do that. And that's what this is. So when B is equal to 6, A is equal to 4. Let's plug in 4 for A and 6 for B. I can solve for the constant C by multiplying both sides by 6. You can think of it as dividing by this fraction 1/6, or multiplying both sides by 6. So over here, you'd have 4 times 6, which is 24. And over here, you'd have C times 1/6 times 6, which is just C. So now you take this constant and you plug it back in here. We get A is equal to 24 times 1 over B. Questions on what we mean when we say inverse proportionality, or how we solve this first example here? Okay. One good example of proportionality problems comes from something called the ideal gas law. Is anybody taking a chemistry class right now? Then let me share this with you. So the ideal gas law is this rule in chemistry which describes the relationship between pressure, volume, and temperature. So it says that the pressure P times the volume V, P times V, is equal to N times R times T. Don't worry so much about what N and R are at the moment. N is the number of moles of the quantity there. T is the temperature, P is the pressure, and V is the volume. Where P is the pressure, V is the volume, and T is the temperature. And this is all about a gas in a closed container. So think about like a scuba tank or something, right? You've got some gas, in that case, like oxygen, nitrogen, in a closed container. It's under a certain pressure. There is a certain volume, a certain amount of space there, and that gas will be at a certain temperature. We can ask a bunch of fun things about this. N and R say they are constants. So one fun question to ask is, are the variables, are the pressure and volume directly or inversely proportional? We could ask, if the temperature goes up, if the temperature doubles without the volume changing, what happens to the pressure? And then one last thing, let's say if the pressure is cut in half, what happens to the temperature? This, by the way, is how air conditioning works in a sense. You've got something going on there called phase change, but it's really about pressures. That's why your air conditioner has a thing in there called a compressor. It puts that coolant under a great deal of pressure, which forces it to change from a gas to a liquid. We're not going to talk about phase change or anything here. We just want to take this equation and try to answer these questions. The challenge, I think, in a problem like this is that they're starting with an equation, but it doesn't look like any of the equations that we've seen so far. It's not solved for one variable. There's a bunch of extra symbols going on. And the trick is just to focus on two things at a time, right? Whatever two things are being asked about. Like in part A, they ask us about pressure and volume. How are pressure and volume related through this? So what I want to do is solve that that equation at the top, the PV equals nRT for pressure, and see how it's related to the volume, because right now these two things are being multiplied. So we're asked, are the pressure and volume directly or inversely proportional? Our first thought looking at it might be that they're directly proportional, because this looks kind of like a direct proportionality thing. There's no division going on in this equation, but it's not solved for the variable we're interested in. It's not solved for pressure. So let me take PV equals nRT and solve it for the variable P. Solve it for the pressure. That would mean dividing both sides by the volume. And this is the same as saying P is equal to nRT times 1 over V, right? Like dividing by 3 is the same as multiplying by 1/3. Having a V downstairs there is the same as having a times 1 over V. And from this expression, we can go ahead and answer part A. Pressure and volume, directly proportional or inversely proportional? What do we think from the bottom purple equation?
Inversely.
Yeah, this is an inverse proportionality thing. Because of the 1 over V here, this means we are inversely proportional. We could also ask, are pressure and temperature directly or inversely proportional? We could ask that question about any pair of variables here. And you would solve for the first variable and see whether the second variable turns out to be downstairs or upstairs. That's all. The next question asks, if the temperature doubles without anything else changing, what will happen to the pressure? So this is something you may have seen someone like throw a paint can on a bonfire. What happens to the paint can when you do that? Maybe your friends were not as stupid as my friends were, but anybody got experience with this or seen YouTube videos? You guys were all angels as children. If you throw a paint can on a bonfire, the paint can will explode. It'll take a little bit of time, but it's a pressure vessel. It's a sealed vessel. And inside you have not an ideal gas, but you have a fluid. As the temperature increases, the pressure will increase to such a point with the paint can that it will explode. Because the walls of the can no longer contain the pressure as the temperature goes up. So if the temperature doubles, that means we're going to replace T by 2T. That's the temperature doubling. And we're going to see what happens to the pressure. So I begin with my PV equals nRT, and I go ahead and do that replacement, and this will become PV equals NR times 2T. And when you replace variables in these proportionality expressions, always with parentheses. Again, there's more symbols here, but it's the same sort of thing as with the area and the radius, or the height and the time. We want to try to find the original expression kind of hiding in here. This is n times r times 2t, which is the same as 2 times nrt. So what's going on here is that if the volume is constant, the volume is not changing, and the temperature goes up by a factor of 2, this right-hand side goes up by a factor of 2. Therefore, the pressure will double. I have a fun question for you. Before we go to part C, thinking a little more carefully about part B. If I double the temperature and I don't want the pressure to change, what needs to happen to the volume? Is there something I could do with the volume here that would allow me to cancel the 2 from this equation? Pressure is going up because temperature is going up. I don't want the pressure to go up though. What do I need to do as I increase the temperature to avoid also increasing the pressure? I would need the volume to go up, right? That's what I would need. You've seen a weather balloon inflate or contract in hot conditions. That's the volume increasing to keep the pressure stable, right? So there's a force pushing out on the balloon. So if you wanted to double the temperature without increasing the pressure, you would also have to double the volume. You'd have to make the thing twice as big. All right, lastly, if the pressure is cut in half, what happens to the temperature? So cutting the pressure in half means replacing P, the pressure, by what? What algebra operation corresponds to cutting in half?
P over 2.
Yeah, we're going to replace P by P over 2. Now here's something you've all experienced, right? When you have a whipped cream canister or what other sort of pressure thing? CO2 canister, anything where you're letting a lot of pressure out very quickly, what happens to the container? When you put a bunch of whipped cream on your pie, what happens to the temperature of the whipped cream container?
Gets cold.
Yeah, it gets really cold. Or if you've ever used those like duster cans, as you spray the stuff out, it gets very, very cold. Even if the can starts off quite warm, that's because the pressure inside is decreasing very quickly, but the volume of the container stays the same. So if we're cutting the pressure in half and keeping everything else constant, we expect the temperature to go down. That's our experience from everyday life. Let's see what we get. I'm going to begin with PV equals nRT, and I'm going to replace P by P over 2. This is the same as 1/2, that same sort of trick, right? Like dividing by B is the same as multiplying by 1 over V. P over 2 is the same as 1/2 P, and everything else stays the same. So again, N and R are constants. So your original temperature, when multiplied by a constant, is equal to P times V. Your new temperature is equal to, has that same constant multiplying it, same PV over here, but now has this 1/2. So what happened? If we cut the pressure in half, what happens to the temperature?
It
Yeah.
decreases.
It decreases. It decreases by a factor of 1/2. So the temperature also gets halved or divided by 2. All right, and this is cool stuff. You can actually experiment with this if you want. I'm sure we have some experience with it. And again, this is kind of what's going on inside your air conditioning unit. There's a compressor that puts the fluid under great pressure, forces it into a liquid. And then there's something called the evaporator, where after the fluid is moved from, is compressed, it's pushed into this thing called an evaporator where it's allowed to expand. And that expansion, that increase in volume corresponds to a rapid decrease in pressure, which corresponds to a rapid decrease in temperature. And then your air conditioner blows air over that evaporator coil, which is now very, very cold, and that chills the air. And then that fluid circulates around, goes back into the pump where it's squished down again, and then it's allowed to expand in the evaporator. It's very, very cool stuff. Okay, so these are about as hard as any of the problems you're going to encounter will get. The ideal gas law has a lot of different symbols and can be kind of intimidating, but none of this is any more challenging than that. I can take one more from your homework before I let you go, just to make sure we feel nice and comfy, and let's make it a tricky one. Something with lots of scary looking algebra. Okay, I think I know which one we're going to do here. So I'm going to give us a few equations. Okay. And I want to think about whether each one of these is describing a direct or inverse proportionality. What is going on in part A? If you had to use some words to describe the relationship between the variables x and y, what words would you use?
A has a direct proportionality.
There is a way to describe this as direct proportionality. This is a fun one. We could say X is directly proportional to y to the -4. That would be a correct statement here, because what we've said is X is equal to some constant 3 times, excuse me, I'm sorry, got COVID, it's terrible. X is equal to a constant times y to the -4. I could also describe this as an inverse proportionality. I could say X is inversely proportional to y to the +4. For what reason? This guy is because this relationship here is the same as saying X equals 3 times 1 over y to the 4. So it depends on what you're labeling as the objects. If I'm talking about just X and Y here, I would say that X is inversely proportional to a positive power of Y, or directly proportional to a negative power of Y. Are we all comfortable with why 1 over y to the 4 is the same as y to the -4? Is that something we've all seen in previous algebra classes? Maybe at the very end here, I'll wrap up with a little list of some algebra rules that we want to remember for this section. But quick, let's go to part B. What's going on there? Is this a direct or inverse proportionality?
Inverse.
Yeah, good. A is inversely proportional to B, right? Because this could be written as A equals 1.6 times 1 over B. So the B is downstairs. All right, part C. What's going on here? This is a direct proportionality. Z is directly proportional to W squared. The last one is fun. What do we think? Direct or inverse?
Direct.
Direct.
Yeah, very good. So Tyson, I haven't heard much from you. That's a good observation. Can you tell me why this is a direct proportionality?
Because you can multiply the y over, and so it'd be x is directly proportional to 2.
Yeah,
Y.
if I multiply the y over, I get x equals 2y. So here, x is equal to a constant times y. So straight up, x is directly proportional to y. All right. This seems like a pretty good place to end for the day. Before I let you go, let me just share with you some algebra rules that I think will show up in this section and will help you. You've probably seen these before. If you remember all the rules for exponents, feel free to leave. But some algebra rules for exponents. Remember, exponent just means power. So if you have two things multiplied raised to some power, you can raise each of those to the power on their own and then multiply them. If you have something raised to a negative power, like b raised to the negative n, that's the same as 1 over b raised to the positive form of that power. if you have a set of, let's say, if you have a raised to some power times a raised to another power, like bases, but different powers being multiplied, that's the same as a raised to the sum of those powers. You can add the powers when you multiply like bases. If you have like bases raised to different powers and you're dividing them, that's the same as subtracting the powers. This is a to the n minus n. There's a partner to this first one. Let me come back here really quick. If you have a ratio raised to a power like that, you can give the power to the top and bottom separately as well. Same sort of thing. And then the last one I'd like to describe for you is just roots. If you take a and you raise it to a power that is a fraction, like m over n, the power upstairs here is telling you to raise a to the m. And then the n downstairs is telling you to take an nth root. And this is sometimes written with this radical notation. And we could do it in the other order also. I could take a to the 1 over n and then raise that to the m. And these are the same. These are all equal to that original thing. And this, in the radical notation, would be the nth root of a, all raised to the m. All right, and then there's one little more, I guess. We can do this too. If you have a raised to some power and you want to raise that whole thing to another power, this is the same as multiplying those powers. So these are all the rules for exponents that you will need, not just in this section, but in future sections as well. Hopefully you've seen this stuff before, but if you haven't, make sure you get this somewhere nice and neat in your notes. You can refer back to it because we will appeal to these rules often, and I want us to be able to do it fluidly without having to think too hard. Alrighty, gang, I'm going to go ahead and let you go here. I hope everybody has a lovely rest of your day. I'll have your partial credit entered for the test by the time we meet on Thursday. You have a homework set you need to be working on. It's homework 9 and quiz 9. Those are both open for you and they're due on Thursday at the start of class. So make sure you get into My Open Math and start working on this direct and indirect proportionality homework and quiz. The other thing I need you to do is to take a look in Canvas at that test 1 reflection. So this will help me decide what to do with our activities and anything to change about the lecture moving forward. Feel free to be completely honest. Let me know what you think. If there's anything that you'd like changed or anything that you think would be helpful for you moving forwards, include that in that test reflection. That would be really nice. And that way I can kind of cater the class to your needs. But that's it from me for today, guys. I hope everybody has a lovely rest of your day, and I will see you on Thursday.